In the last video, we learned this new integration technique called integration by parts. And the big takeaway was a formula told you that the integral of u dv is equal to uv minus the integral of v du. Gave us this new formula that's a way of kind of, loosely speaking, undoing the product rule. And I went over all that in the last video. Really, the purpose of this video is just to get a lot of practice. And not even that much practice. I got 3 examples that I want to go over. Because what you'll see are integration by parts problems that kind of take a little while. And sometimes they can be really involved. And I think 3 examples will end up being plenty for this video. So let's give it a shot. We have this formula, which eventually you'll want to have memorized, but for now I'll write it up here just so we have it handy. And let's try to use it to figure out the integral of x divided by e to the x dx. So the first thing you might notice here is this formula works when you have multiplication. And we don't have multiplication, we have division, right? This is x divided by e to the x. I wish it were x times e to the x. It would fit this a lot better, but it's not. Fortunately, there's something that we can do to change division into multiplication. What we're going to do is take advantage of negative exponents. 1 divided by e to the x power is the exact same as e raised up to the negative x power, because negative exponents just mean take the reciprocal of. So x divided by e to the x is the same as x e to the negative x, so the integral of x over e to the x dx is the same as the integral of x e to the negative x dx. So the first issue with this example is, as we've seen, sometimes the question is not in a form that's conducive to the rules that we have. However, with a little bit of cleverness, changing division into multiplication, it fits this a lot better. The next challenge that we have is properly picking u. We have 2 factors here, x and e to the negative x, and we have to decide which one of those 2 things should be equal to u. What's left over after we choose u will be dv, and after we figure out u and dv, we'll have to figure out du and v, but that'll be the next step. So what should u be equal to? Well, we got 2 choices. We can either make it x or e to the negative x. When you're just learning, you might want to try it both ways and see which one works. However, a little hint that I can give you is generally, you want to pick the thing for u so that when you take its derivative to figure out du, it gets simpler. What do I mean by simpler? Well, it's a bit vague, but if you think about this new integral is going to be v times du. So this new integral will be the antiderivative of what I put over here times the derivative of what I put over here. So I want to choose something over here so that its derivative gets simpler, and I want to choose something over here so that its antiderivative doesn't get more complicated. Because generally, derivatives make things nicer, but antiderivatives make them uglier. So because my goal is to choose something for u that'll make du so much nicer, I'm going to let u be equal to x. Because look, if u is equal to x, the derivative of u would just be equal to 1, so du would just be equal to 1 dx, or just dx if you want. There's not a whole lot simpler when I'm trying to take antiderivatives than just having a 1 sitting right here. If u is equal to x, then what's left, e to the negative x dx, is what I would have in place of dv. I've already figured out du, so all that's left is for me to figure out v. v is the antiderivative of dv. So I got to think about what function could I have up here so that when I took the derivative of that function, I get e to the negative x. And you might be thinking, well, isn't it just e to the negative x? Not quite. Because if you take the derivative of e to the negative x, you'd have to use the chain rule, right? E raised up to stuff is e to that stuff times the derivative of that stuff. The derivative of the negative x would produce an extra negative 1. But I don't want that negative 1, so what I have to do is put something here so that when I bring the negative 1 down in front, that negative 1 goes away. The way I'll do that is by putting a negative 1 down here. Can you see how that would work? If you take the derivative of this thing, you leave the negative 1 alone, and multiply that by the derivative of e to the negative x. The derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1. That extra negative 1 and this negative 1 cancel, and I get this e to the negative x. The antiderivative of e to the negative x is negative e to the negative x. There's a decent chance that that confused you. If that confused you, you're not alone at all, and what you can do is think about the process of finding v is like a problem inside of a problem. Figuring out v is equivalent to taking the integral of dv, e to the negative x dx. So think about if you started with this problem right here, what would you do? Well, if this showed up in the last section, maybe what you do is think u substitution. Maybe you'd let u be equal to negative x in which case du would be equal to negative 1 dx. And since I don't have a negative 1 dx in here to substitute in, I could multiply both sides of this equation by negative 1 and get negative 1 du is equal to dx. I can now use this top line and this third line to substitute in here and rewrite this integral as the integral of, instead of e to the negative x, e to the u power, and then instead of dx, negative 1 du. This is an integral I can evaluate. Because negative 1 is just a constant, I pull it out in front of the integral symbol, and I have to figure out the antiderivative of e to the u du. Great thing about e to the u du is its antiderivative is just e to the u. So I get negative e to the u plus c, technically, as the antiderivative here. We don't have to worry about the plus c part. All we have to do is change our u's back to negative x's, and we get negative e to the negative x, again, plus the c technically, as our answer. This negative e to the negative x is what ends up going in place of this v. A big challenge with this integration by parts method is inside the integration by parts method, you got to remember derivatives, think back to chapter 2, and you also have to do antiderivative problems. And sometimes those antiderivative problems are basic, and sometimes they involve a long method like u substitution. You'll probably get to the point where you can look at this and tell that this is its antiderivative, either directly or by doing kind of a guess and check method. But in case you can't, if you want something written down more concretely, here is how we could figure out that this is what goes in place of v. So that's my answer? No. All this does is gives us the pieces that we're going to use in our integration by parts formula. The integration by parts formula tells us that the integral of u dv is equal to u times v, so x times negative e to the negative x, minus the integral of v du. So minus the integral of negative e to the negative x times 1 dx, or just dx. The good news is this is an integral that can be cleaned up a little bit and then evaluated. I got negative x e to the negative x, and then I can bring this constant of negative 1 out in front to make this plus the integral of e to the negative x dx. I've changed this integral, x e to the negative x, which is really challenging, into this integral e to the negative x, which is not nearly as challenging. If I could figure out that integral, I'd be done with the problem. And good news, you can figure out this integral. How do I know? Because we've already done it right here. The antiderivative of e to the negative x is negative e to the negative x, plus c technically, for the same reason that we got this v from this dv. For the same logic that we did in pink here, we can change this integral into this expression. That gives us our final answer here. This was meant to be an easier example of integration by parts, but what you see with integration by parts is they're kind of challenging, right? Even this problem that didn't really look all that ugly ended up being really challenging, kind of depending on how comfortable you are coming up with v from this dv. Let's try another one. What if we're trying to figure out the integral of 3x squared e to the 4x power? The first thing I would advise you to do here is don't forget the things that you've learned previously. This 3 is just a constant. There's no reason we can't pull this 3 out in front of the integral symbol and evaluate the integral of x squared e to the 4x dx. You don't have to do that, but it might help you, generally speaking, to pull constants out in front and make things look less complicated. I'm now ready to use my integration by parts. To use integration by parts, I got to figure out what u should be equal to, and then what's left over will be my dv. My options for u are either x squared or e to the 4x. If you think about those two things, the x squared will get a little bit simpler when I take its derivative, but e to the 4x will not. So my choice for u is going to end up being x squared. If you're not comfortable with that, try it both ways and see what happens. If u is equal to x squared, then dv is e to the 4x dx. With these choices of u and dv, I can figure out du and v. Du is the derivative of u. The derivative of x squared is 2x dx. V is the antiderivative of dv. The antiderivative of e to the 4x is 1/4 e to the 4x. Wait, where'd that 1/4 come from? Well, think about if you were taking the derivative of this. The 1/4 is a constant, so you leave it alone. The derivative of e to the 4x is e to the stuff times the derivative of that stuff. When I take the derivative of 4x, that produces an extra 4. I need this 1/4 to cancel out that extra 4 to get me back down here to the e to the 4x. It's very similar to how we came up with this negative e to the negative x from e to the negative x. We're really doing a u substitution here, where u is equal to 4x. If you're not comfortable coming up with this value of v, evaluate the integral of e to the 4x dx by doing a u substitution where u is equal to 4x. And I think what you'll find after a few steps of work is that that's equal to 1/4 e to the 4x plus c, and that 1/4 e to the 4x is what I'm putting up here for the v. Anyways, I got these 4 pieces of information, so I can use my integration by parts formula. My integration by parts formula tells me that the integral of x squared e to the 4x, so I need 3 to be multiplied by this entire thing, the answer that I get here, is u times v, which I'll write as 1/4 x squared e to the 4x, minus the integral of v du, which I'll write as 1/4 times 2x e to the 4x. This is kind of ugly looking. First, make sure you can follow all the moving pieces. Then think about how you could clean this thing up. Got a lot of constants floating around out here. Maybe I could pull those constants out in front of the integral. I'm going to leave everything out here alone for now, although if you wanted to clean that up, you could. And then I'm going to think about 1/4 times 2 is just 1/2. And I'm going to pull that 1/2 out in front of the integral, so I get minus 1/2 the antiderivative of x e to the 4x dx. I got good news and I got bad news. What we have left in the integral here, x e to the 4x, is simpler than what we started out here, 3x squared e to the 4x. That's the good news. The bad news is the integral of x e to the 4x is not something that we can immediately figure out. What we're going to need to do to evaluate the integral of x e to the 4x dx is use integration by parts. What, again? Yeah, because think about it. You got something times something. We could let u be equal to the x, in which case the du would just be 1 dx. And if the u were the x, what we'd have left over for the dv would be e to the 4x dx. As we've seen already, when dv is e to the 4x dx, v is equal to 1/4 e to the 4x. It's the same choice of dv and v that we had up here in green, so we can reuse the work that we've already done. The integration by parts formula tells us that this integral right here is equal to u times v, which I'll write as 1/4 x e to the 4x, minus the integral of v du, which is 1 times 1/4 e to the 4x dx. In other words, 1/4 e to the 4x dx. The bad news is we still have an integral here to evaluate. The good news is finally it's an integral that we can deal with. Let me first clean things up a little bit. My full answer is 3 times 1/4 x squared e to the 4x minus 1/2 times 1/4 x e to the 4x. I could take this 1/4 and pull it out in front to make it minus 1/4 times the integral of e to the 4x dx. And then all I have left in the integral is e to the 4x. What's the integral of e to the 4x? What's the antiderivative of e to the 4x? We've done that a couple of times already. The antiderivative of e to the 4x is 1/4 e to the 4x. The antiderivative of e to the 4x is 1/4 e to the 4x. So I take this 1/4 and I bring it out in front of the integral, and what's left is the integral of e to the 4x, which is equal to 1/4 e to the 4x. Close a bunch of parentheses, tack on my plus c, and I'm done. What happened in this problem is we had to use integration by parts twice in a single problem, first in green and then in blue, which is kind of wild and can make it really easy to get lost in your steps and what you're doing, which really emphasizes the need for showing your work really neatly and spacing things out, neither of which I've done in this example. This final answer, you could definitely clean it up by getting rid of some parentheses if you felt like it. In fact, I think I'm missing a set of parentheses right here. But I don't think I want to do that. I don't think I want to waste your time having you watch me distribute fractions into fractions. Why don't we just call this a good answer and move on to the last example in this video. And maybe I can do a better job of organizing my thoughts with this one. This problem, I don't know. I don't think it's reasonable to ask a student to recognize what we're doing on this problem. So maybe it's not one that you could solve on your own, but maybe it's one where you can like watch me do the steps and follow my logic. The problem with this problem is, yeah, it's something times something, x to the 11th plus x to the 5th times the natural log of x to the 6th plus 1. But each of those things are so ugly that if we tried to use the integration by parts formula, no matter which one we called u, it would get pretty ugly figuring out the different parts. There's a trick to this problem, and the trick to this problem is recognizing that each of these terms right here have an x to the 5th in them. So you could, I'm not saying you should have recognized this, but you could rewrite this first factor as x to the 5th times, if I pull out an x to the 5th from each of these guys, x to the 6th plus 1. So instead of x to the 11th plus x to the 5th, I got x to the 5th times x to the 6th plus 1. And that's being multiplied by this natural log of x to the 6th plus 1 dx. And if you somehow, by some miracle, happen to see that, maybe then you'd recognize that, well, I got an x to the 6 plus 1 over here and an x to the 6 plus 1 over here. That shows up twice. And this x to the 5th is kind of like the derivative of x to the 6 plus 1. Maybe if you wrote this, you might think to do a u substitution. You might think to let u be equal to x to the 6th plus 1. If you made that realization, then du would be equal to 6x to the 5th dx. And if we multiplied both sides of the equation by 1/6, we'd get 1/6 du is equal to x to the 5th dx. And all of a sudden, my pieces are going to fit really nicely. This whole thing will turn into a u, this will turn into a u, and this will turn into 1/6 du. What I'm saying is, with this clever u substitution, we can rewrite this problem as the integral of u times the natural log of u, and then we can replace the x to the 5th dx with 1/6 du. This 1/6 is just a constant, so I can pull it out in front and get 1/6 times the antiderivative of u, natural log of u, du. Good news and bad news. The good news is this is significantly easier to take the antiderivative of. Bad news is we're going to need to use integration by parts. We got something times something. A challenge with using integration by parts right now is we've kind of already used up the letter u, right? Which is a bummer because that's going to get really confusing when in a minute I write let u equal u and let dv equal the natural log of u. I mean, you can do that, but just so you don't get confused, you might want to change your letters here. You might want to make this, I don't know, pick any other letter you want. W maybe. W times the natural log of w dw. Just change all these u's into w's so that when we use integration by parts up here, things aren't quite as confusing. For integration by parts, I have to choose what u should be equal to, and I have to choose what dv should be equal to. I have two things here, a w and a natural log of w. If I choose w for my u, then the natural log of w will be my dv, and I'll have to figure out the antiderivative of the natural log of w. And unfortunately, we don't know how to do that. So what we're going to have to do is let u be equal to the natural log of w, and then what I'm left with for dv is just w dw. If u is the natural log of w, then du is 1 over w dw. And if dv is w dw, then v is equal to 1/2 w squared. Because the antiderivative of w is 1/2 w squared, because the derivative of 1/2 w squared is just w. With these four pieces of information, I can use integration by parts. I still have this 1/6 out in front, and then I got the integral of u dv is equal to u times v, which I'll write as 1/2 w squared natural log of w, minus the integral of v du, 1/2 w squared times 1 over w dw. This might look like a big mess, but I think it's going to simplify really nicely. I'll leave these big parentheses in here for now. We'll take care of that later. In fact, I'm going to copy everything down until I get to my integral here. The 1/2 I can pull out in front, and what that leaves me with inside the integrand is w squared times 1 over w. But the 1 over w cancels with one of the w's in w squared, and so what I'm left with in my integrand is really just w dw. The antiderivative of w is something that's easy to figure out. In fact, we've already done it up here. The antiderivative of w is 1/2 w squared, so I have this 1/2, and then I have another 1/2 w squared plus c. Could leave your answer like this if you want. This time what I'm going to do is get rid of all the parentheses, so take the 1/6 and distribute it through to get 1/12 w squared natural log of w minus 1/4 times 1/6, or 1/24 w squared plus c. You don't have to do that last step. Sometimes I just can't help myself to simplify some expressions. So if you're ever making math videos and you want some advice, my advice is this. If you're going to forget to do something, forget to do it at the end of the video. And that way, at least you don't have to go back and re-record the whole thing. So here I am realizing that this is not my final answer, right? Because the original question didn't have w's in it. W is something that I introduced really to take the place of this u, which came from this u substitution. So really this final answer here, each of these w's should be changed into x to the 6th power plus 1, which gives me this answer in red as the final answer, not this answer in dark blue. Anyways, the point of this problem was supposed to be, sometimes you end up with a huge mess and it's really challenging to know where to start. But with the clever u substitution, you're left with something that very nicely fits the integration by parts formula. In this video, we've seen a more basic, although it wasn't easy, integration by parts problem, and then we've seen an integration by parts problem that involved 2 iterations of our algorithm, and then we saw an integration by parts problem where we had to first do a u substitution. So lots of variety on the integration by parts stuff. There's a few little pieces left over, but I feel like that deserves its own video because this one's pretty dense.